Oh, great. Again, it does not show this. Okay, so I think my entire desktop is visible right now.
Yes.
Okay.
Yes.
So if you remember at last time we talked about partitions of n, and so this is what we did. Given this sort of a partition, we talked about Ferret's diagram, which is a dots, like collection of n dots, and then number you see in the first location here is the number of dots you put in the first column, and so on. Okay. Sorry, what am I drawing? Oh, God. So the number you see here is the number of dots in the first row. Number you see here is the number of dots in the second row, and so on. And when these dots or circles are replaced by squares, you call this diagram as Young diagram. Okay. And then we also talked about some properties of this sort of a diagram, which were that all of this, since it is left aligned, okay, we started drawing the dots starting from the left, and this lambda is a partition, which means any lambda I is greater than lambda j if I is bigger than j, right? So they are in the non-increasing order, which means this entire thing, this entire diagram, if I take an axis here, the main diagonal here, and reflect it along that particular axis, then also I get a diagram of similar kind. What does that mean, similar kind? That it will be a left aligned diagram. And if I write the corresponding lambda prime will have this property again, that it will be a partition of that same number, and also it will be written in the non-increasing order, right? Right?
Yes.
Okay. So this all we talked about last time. And then we said, okay, yeah. So what is the main property that you get about this new lambda prime, and how well can you understand lambda prime in terms of lambda is the first topic for today's lecture. And then we'll shift to something called the 12-fold way. So the 12, okay, we'll see that later. Okay, I think I scanned again. Huh? Okay, so this lambda prime, which you obtain from lambda by reflecting it along the main diagonal, is called the conjugate partition of lambda. Okay. So lambda was one partition, and then you have the conjugate partition for this lambda to be this lambda prime. The lambda prime is obtained from Ferret's diagram by interchanging the rows and the columns. Right? That is what it really asks when you say that reflection along the main diagonal, you make rows to be columns and columns to be rows. Right?
Yes.
And remember that this representation actually means that 5 plus 5 plus 4 plus 2 plus 1 is 17. So this plus this plus this plus this plus this is 17. Now when you have flipped it, it is going to appear in this pattern, right? So what it really says that if lambda happens to be lambda 1, lambda 2, lambda 3, and so on, then the number of parts of lambda prime which are equal to I is exactly lambda I minus lambda I plus 1. Because exactly those many places this I would survive, other places this I would become 0. Right? Therefore, if you take lambda to be 4, 3, 1, 1, 1, then to determine lambda prime, you start from this. So number of parts of lambda prime which are equal to 1 is lambda of 1 minus lambda of 2. So 4 minus 3, which is 1. Number of parts of lambda prime which are equal to 2 is going to be this minus this. So there are two parts which are equal to 2. There is exactly one part which is equal to 1. And there are no parts which are equal to 3. And there are no parts which are equal to 4. Okay. And can you have a bigger thing? No, because this has exhausted already. Now, oh, I mean, this is not how I should say. Oh, God. So, how many parts of lambda prime are equal to 2? There are two parts, which means 2 appears twice in the presentation of lambda prime. How many times would 1 appear?
1.
Once. So 2 appears twice, 1 appears once. Now what is really left with you? That has to appear just once. So add them up. You have 2 plus 2, 4 plus 1, 5. And what was the total here? 4 plus 3, 7 plus 3, 10. Which means there is exactly one part of lambda prime which is equal to 5. And so the partition which corresponds to this particular lambda prime is 5, 2, 2, 1. Okay. All other parts would have come from here, right? So whatever is left at the end is the largest part here. And that you can retrieve from the information of what is the number whose partition this particular lambda is minus what are all other parts which you have achieved here. So there is part 1 which you have achieved once, there is a part 2 which you have achieved twice, there is a part 3 which occurs 0 times, and the part which would have value 4 appears 0 times. Am I clear?
Yes, ma'am.
Okay. So this way lambda prime turns out to be 5, 2, 2, 1. Now, if you recall, pkn was a number of partitions of n which had exactly k many parts, right? We did this in the last lecture, or probably last lecture, when we did pn, pkn, and p of j comma k comma n.
Yes, ma'am.
Everyone remembers that? So, just as pk of n, let's say p less than equal to k of n be the number of partitions of n which has at most k parts. So this collects all those partitions of n which probably have 0 parts, which we know is 1, which will have 1 part, which also we know is 1, which possibly has 2 parts, and so on till k many parts. So p less than equal to k of n is this particular number, right? Right?
Yes, ma'am.
Okay. So now, when you say that lambda has at most k parts, what does this really say about lambda prime? So come to this diagram again. Lambda have, let's say, so here you have 5 parts, right? Right? So if you have 5 parts, which means you would have had 5 rows here, correct?
Yes.
And now when you see this diagonally, then this is what you see. So you will see a 5, 4, 3, 3, 2. Correct? That will be your lambda prime. So what is this number
Yes.
really?
Number of parts of lambda, which
Exactly.
is the
So this is the
first
number of
number of
parts of
lambda.
lambda, and it is also the largest part of lambda prime, because now you're reading it this way. Isn't that so?
Yes.
So what we're really saying is that the number of, if lambda has at most k many parts, then lambda prime has largest part to be at most k. Correct? Correct?
Yes, sir.
So lambda has at most k parts is this, right? So whichever lambda is there with at most k parts is the one which gets counted here, right? So now we will try to deduce this particular problem to a different problem, and the way of doing it would be that you deal with the two sides of this equality in two different ways. Okay, so you understood that lambda has at most k parts is equivalent to saying that lambda prime has largest part to be at most k, and such lambdas are exactly the lambdas which gets counted here. So instead of looking at this and dealing with this, we are going to deal with this and put here and arrive at a generating function for this particular function. Okay.
Okay.
So can we find the generating function for p less than equal to k of n? Yes, and the way of doing it is this. So, so this I've already said. So what it really does is that if you take any partition of n that gets counted in this particular number, it's actually a solution in the non-negative integers to this following equation: m1 plus 2m2 plus so on till k mk equals n, right? Where mi is actually the number of times ith part is appearing in your lambda. Okay, so if lambda has k parts, you actually hit till k mk, otherwise you would have stopped somewhere earlier itself, right? So you see how many equivalent interpretations I have for this entire thing. So p less than equal to k of n in the most obvious sense is this number. And this number counts these lambdas. These lambdas are equivalent to these lambda primes. And any point here actually corresponds to a solution to this equation. Okay. And now any lambda here, which is looking like this, if you remember, we had done this particular notation that something like this equals n, such a partition is written as 1 raised to m1, 2 raised to m2, and so on, k raised to mk. Correct? Correct?
Yes, sir.
So now we have shifted to multisets, right?
Yes.
Great. So if you look at the generating function, p less than equal to k of n, q n, This is summation n greater than equal to 0, summation qn, and this summation runs over this n, right? So this, which is the lambda, correct? So this is m1 plus 2m2 plus 3m3 and so on till kmk equals n. You run your q raised to n over this summation. But now doing this is same as taking m1, m2 and so on, all of these, you have collected all these values since n is varying from 0 and so on till infinity. Putting this particular thing equals n, so both these summations together actually gives you this individual summation m1 greater than equal to 0, summation m2 greater than equal to 0. So you basically have, also the dots are not visible here, there are dots here. So you have the product of all of these summations, okay, and q raised to this particular n. So n inside is actually the m1 plus 2m2 and so on till kmk, correct? And now since this particular inequality is free of, this particular summation is free of m1, m3, m4 and so on till mk, so is this free of m2, m3 and so on. So you do this manipulation and you get that this is indeed is equal to summation q raised to m1, summation running from m1 greater than equal to 0, summation q raised to 2m2 and m2 running from 0, and so on, summation q raised to k mk, mk running from 0 onwards. So what is this number? What is this power series? What is 1 plus x square plus x cube plus x4 and so on is equal to?
Minus x.
Sorry?
1 by 1 minus x.
1 by 1
Here
minus x. Similarly, what is going to be 1 plus q square plus q4 plus q6 and so on?
1 by 1 minus q square.
1 by 1 minus q square and so on. Similarly, this is going to be 1 by 1 minus q raised to k, right? So, okay, so I have written it this way. So this actually turns out to be 1 upon 1 minus q square and so on till 1 minus q raised to k. So you see how elegantly you have figured out that the generating function for p less than equal to k is this. Yeah.
Yes.
Now, if we see this the other way around, which is that if I am asked that find the coefficient of q raised to n in this particular huge rational function, what will you tell me? Yeah. What is the coefficient of q raised to n in this? What is this thing equal to, by the way? Yes, people. Isn't this thing equal to this?
Yes, ma'am.
So, this as a series is equal to the series which will correspond to this.
Yes.
And when are two series equal?
when their coefficients are equal at all stages.
Coefficients are equal, corresponding coefficients. So when I ask you the coefficient of q raised to n in this series, what should be the answer?
P less than or equal to K.
P less than equal to k of n. So finding the coefficient of q raised to n in this is equivalent to finding the number of partitions of n with at most k parts. Isn't that so?
Yes, ma'am.
So big problem solved. Now you know what I will ask in the quiz. Or you know what I will precisely not ask. Okay. Moving forward, if you let your k to tend to infinity, which means you do not really restrict the number of parts this will have, what it takes, it can have all possible products, right? Depending on the
Yes.
n. So when you let k tends to infinity, then you are actually counting all the partitions rather than just saying partitions with at most k parts. You're counting all the partitions of the n, and that turns out to be the product of these many rational functions. Okay. After this, we shift to the next topic for today, which is the 12-fold way. So this is very interesting. What really is this 12-fold way is? So all of you have had some information or some knowledge of probability.
Yes.
People understand mutually exclusive, mutually independent events, etc.
Yes. Yes, ma'am.
The addition rule, the multiplication rule, etc.
Yes.
Great. So if I tell you that certain event has to happen in two phases, first phase can happen in 3 ways and second phase can happen in 15 ways, in how many total ways can this entire function take place?
45.
What numbers did I say? First phase had how many?
3 and 15. So 3 times 15, because we can choose the fast in 3 ways, and for each of them we can choose the second in 15 ways.
Okay, I said 15. I thought in my head I said 5. So, yeah, Ridhiman is right. We will have 45 ways of conducting this function. Correct? Everyone
Yes.
understands this, right? Or is there any confusion?
Yeah, this is fine.
It's fine. Great. So, this 12-fold way is about counting the number of functions from one particular set to another particular set. Okay, both finite sets. And then depending on whether the events in each phase are you know uh, if they can be distinguished from one another or not, it would make a difference. For example, if let's say you say the phase 1 has dance competition and a singing competition, then these two you made as distinguishable, right? Right.
Yes.
In contrast to if you say first phase will have 4 dance competitions, Which way does not really matter. There are just like there are some 40 teams, and they have randomly been divided into 4 parts. So there are 4 different parts, and which part happens when does not really matter. All that matters is that one particular part consists of 10 teams, and those 10 teams have to compete with each other in that dance competition. So then I still have 4 events in my phase 1, but these 4 events are indistinguishable. Correct? Similar things can
Yes.
happen for things in the phase 2. Now, this was all this, hoping that you people have some cultural this thing. I keep seeing some e-summit or something emails coming up. So I thought maybe that's a good way to motivate you. But coming back to business, you have to count the number of functions from n to x. N has cardinality n, x has cardinality x, and then there are some restrictions. Not really f, but this entire business of having these functions, uh, this counting happens under certain restrictions. Okay, so there are 3 types of restrictions on the function f, and then there are 4 types of restrictions on when to consider some two such functions to be same or not same. So this is suppose your phase 1. So you have 3 types of constraints here, and there are 4 restrictions on the type when you would consider two such elements coming from this set to be equivalent or not equivalent. So how many total ways are there for these type of countings? As in, how many different types of functions can appear? Don't tell me the number of functions, different types of functions.
Ma'am, can you repeat the question? I didn't get it.
So you understood till here that we are going to count the number of functions that are there from the set n to the set x under certain restrictions. This
Yes.
particular
Yeah.
thing is wrong. This is not there. Okay. So forget about this. Under certain restrictions. Now, these restrictions appear in 2 types. First type is that there are 3 types of restrictions on the function f itself. And the second type of restriction is that there are, so given, once you have taken these 3 types of constraints on f, okay, if you deal inside one of these constraints, let's say let's say there are 3 types. So f1, f2, f3. Okay, 3 major classes of functions are there now. Now within the f1, let's say when you are there, when would you say some 2 functions f1 and g1 are same?
We want an equivalence relation on other class F1
Yes,
of function.
yes. So along with this constraint and with this constraint, in total, how many equivalence classes are there in which all these functions from n to x can be classified?
D12.
12. 3 types coming from here, 4 types coming from here. Both of these are mutually independent. So you have 3 into 4, which is 12. Okay. So this gives a 12, this gives a total of 12 counting problems. So, I mean, once you are in one particular equivalence relation, equivalence class, counting all those is one counting problem. Then you shift to the new equivalence class and then count all the functions there. That is the second counting problem, and so on. So there are how many? total of 12 counting problems. And the solution to this whole sort of setup which you have put in front of you is called the 12-fold way. This 12-fold way, that is why the name, because there are a total of 12 equivalence classes which you are dealing with inside this one huge class of functions. Okay.
Yes, ma'am. What kind of constraints are you thinking about in the first
No. So that
on
is
F?
that you will figure out in the treasure hunt whenever CMI opens. Okay, so we will give you hints and clues and you have to figure out what are these constraints. Okay.
I see.
So coming down to the type of constraints you will have on a function. First is you do not put any constraint, which means f can be any arbitrary function. Second is this function f has to be injective. Third is f has to be surjective. Okay. So all these
Okay.
are functions. Yeah, well-defined functions. So you can have a function without any restriction, just a well-defined function is fine. Or you can ask that I want my function to be injective, or you can ask that my function should be surjective. So these are the three restrictions on the function itself. And then now we'll see the four types of restrictions on the set when f and g should be considered same. So for this f and g to be same, let's do some work. So this really happens depending upon whether the elements of this set or elements of this set are considered distinguishable or indistinguishable. Right? If you can distinguish elements of this set or not, if you can distinguish elements of this set or not, that gives you when these two functions would be considered same or not. So the set n can have elements distinguishable or non-distinguishable. So there are how many types? Two. Correct? Similarly for this, there are either the elements of X are distinguishable or they are non-distinguishable. Right? So how many pairs are possible? Let's say distinguishable stands for D, indistinguishable stands for I. Then you could have a DD, DI, ID, or II. Right? So there are four possibilities depending on whether
Yes.
the elements of n and x are considered distinguishable or non-distinguishable. Now, pictorially, if we want to understand this, let's say the elements of n are balls and the elements of x are boxes, and you consider this you consider these four functions f, g, h, I from the set n to the set x, where n is 1 to 3, x is ABCD. So f sends 1 to A, 2 to A, 3 to B. G sends 1 to A, 2 to B, 3 to A, and H and I similarly. Now, if you want, if you are in the, so remember I said consider the distinguishable to be D, indistinguishable to be I. So if I am with the pair D comma D, which means all the balls are distinguishable as well as all the boxes are distinguishable, then this sort of data I can represent pictorially in this fashion. So there are four boxes A, B, C, D. So each box has a label. One box has a label A, one box has a label B, one box has a label C, and one box has a label D. Right? So there are four distinct boxes. Okay, this particular box has label A, this particular box has label B, this has label C, and this particular one has label D. Now F sends 1, the ball numbered 1. So it's like how you would really play in a, you know, this billiards game. So the balls are numbered, and you are saying the ball with number 1 goes to box A. So you send the ball with number 1 to the box A. So this is my box A. Then 2 also goes to box A. So 2 also I have put in the box A. 3 goes to box B. So this was the box B. So here I have put my 3. C and D remain empty. Doesn't matter to me. Now, if I come to the function G, it sends the ball 1 to A. So I've put 1 in my box A. Then 2 goes to the box B. So I've put 2 in the B. And then A in the, 3 in the box A. So 3 again I have put in A. Again my C and D are empty. Doesn't matter. So this is my function F. Pictorially, this is my function G. Now coming to H, it sends ball 1 to the box B. So I've put it here. Ball 2 to the box B. So 2 also comes here. Ball 3 to the box D. So 3 comes in the box D. So you don't see a box here. Actually, I didn't realize I should have left a line in between. इसलिए मैंने बाकी boxes नहीं बनाया. But you understand the thing here, no? So my function H sends ball 1 and ball 2 in the box B, ball 3 in the box D, and boxes A and box C are empty. Similarly, when you deal with the function I, it is sending ball 1 to the box C here, and now ball 2 and ball 3 both come to box B. So here. Fine. So all
Yes.
of these 4 functions look different. What does it mean when I say look different? No two functions will have same boxes having same balls. Right? Is that right?
Yes.
Great. Now in the same picture, you see this particular box corresponding to A has 2 balls here, and corresponding to B it has a 1 ball here. Similarly, the function G has 2 balls in the box A and 1 ball in the box B. Now, if I had to forget the names written on my balls, then all I would be counting is that, see, the box A has 2 balls, ball B has 2 balls. So this and this will look same then,
Yes.
right? So that is the case when my n elements of n are indistinguishable while the elements of x are distinguishable. So that will be the pair I comma d. So okay, all pictures are different from each other, so is each function. So if the elements of n are non-distinguishable while the elements of x are distinguishable, this is the picture you get. So are you able to compare? So see, there were 2 balls here, 1 ball in the next. So 2 balls here, 1 ball in the next. Then 2 balls here, 1 in the next, 2 balls here, 1 in the next. Then A was empty, 2 balls in B. C was empty, 1 ball in D. A is empty, 2 balls in B. C is empty, 1 ball in D. Right? I am just forgetting the names written on my balls. Then this is the picture which I get. So box A has 2 balls, box B has 1 ball for both the functions f and g. And extending further, the boxes corresponding to the C and D remain empty in both the cases. Right? So this picture is exactly equal to this picture. Therefore, in this scenario, we say that the function f and the function g are equivalent. When the elements of n are not distinguishable, but elements of x are distinguishable. Okay? Is that okay?
Yes.
Consume this within and then like we can proceed further. Or shall I move?
Yes, ma'am, it's okay.
It's okay, great. Now I will do the reverse thing, which means I will take the elements of x to be non-distinguishable and elements of n to be distinguishable, which means what do I have to forget now? I have to forget the labeling of the boxes. And I have to remember the labeling of my balls. Correct? Correct?
Yes.
So, what I would say, F sends ball 1 and ball 2 to one particular box, ball 3 to another box, and two boxes it leaves empty in the language, right? Function G sends the ball 1 and 3 to a box, ball 2 to a box, and two boxes it leaves empty. Function H sends 1 and 2 to a box, 3 to another box, and two of the boxes it leaves empty. I sends 2 and 3 to a box, 1 to another box, and two of the boxes are empty. So which of the two functions are same now? Equivalent? Let me show you. So here is the ball. Here's the picture.
F and H are equivalent, right?
F and H are equivalent because how you put the boxes is irrelevant now because there is no labeling. So whether this box comes here or this box goes there does not really make a difference. All that matters is that the balls 1 and 2 goes to the single box, ball 3 goes to a different box, and two of the boxes are empty. Okay, so F and H becomes equivalent in this scenario. Now the last choice, which was that X, elements of X are indistinguishable, elements of N are also indistinguishable. Then what does F do? F sends two balls to a box, one ball to another box, two boxes empty. G sends two of the balls to one box, one ball to another box, and two of the balls are empty. Boxes are empty. H sends two balls to one box, one ball to another box, and two boxes are empty. I also does the same. So when the elements of n and elements of x both are indistinguishable, then which functions are equivalent?
All
All four functions become equivalent. That is what we have written here. So if elements of n and x both are indistinguishable, then all of f, g, h, and I become equivalent. So this is in this particular case. Okay, do not confuse it with the in the sense that whenever you consider any set of functions from n to x, regardless of n and regardless of x, if the elements of both of these sets becomes indistinguishable, then all the functions are going to be equivalent. That is not the case. This is happening only for these particular functions here, right? Here itself, if one of the functions was injective, then you could not have achieved this, correct? If it would have sent one ball, if it would have sent so that one box contains at max one ball, then you would not have gotten all the functions to be equivalent, correct?
yes.
Say something.
Yes.
Okay. So formally, what does what does this say? Two functions f and g from n to x are said to be, STB is said to be equivalent with and indistinguishable if there is a bijection U from the set n to itself such that f of u of a is g of a. Right? So there is a sort of involution happening in between. So an element of f is sent to an element of g through this bijection u. Right? And this happens for every element. So this is a sort of just relabels what your f of a was, or what your what your g of a was. Correct? So when you are able to do such a bijection between these two elements, f and g, you say these two are equivalent. Okay. Similarly, when you consider, when you want to look at f and g from n to x to be equivalent with x indistinguishable, here we were dealing with n indistinguishable. Now you say if x is indistinguishable, this would happen only if there is a bijection v from x to x such that what f would have taken a2 and what g would have taken a2, that is involuted through my function v. And this is now a bijection. Okay. So once there is a bijection between the balls, another time there is a bijection between the boxes. You are swapping the boxes or you're swapping the balls. Right? And swapping can happen only when you treat the elements to be indistinguishable. So makes sense. Correct?
Yes.
Now, two functions f and g will be equivalent with n and x both indistinguishable now if you have bijections u from n to n, v from x to x, such that you swap the elements in n, which is the boxes, and then you take the f of it. So now you have landed into boxes. So sorry, u of a were the balls. Okay, so you have swapped the balls, and then f of that element is going to land you to a box, and g of a is already a box. So now these two boxes are swapped through this involution v on x. If they happen to be same, then you consider f and g to be equivalent. Okay. So are you people familiar with this swapping and rotation business? I
No,
mean,
ma'am,
it's
not
just
really.
relabeling.
Yeah.
Like a very simple example, if you have to you have two particular integers x and y and you want to interchange their values, you take a new variable, let's say z, you assign x to z, and then z is y is assigned to x, and then z gets assigned to y, so that the thing which z does there is exactly the things which u and v are doing here. Okay.
Yes, ma'am.
So exercise for you people is that, so here we have three types of equivalences on the set of functions. you have to show that all of these notions of equivalences are actually equivalence relations. Okay?
Yes, miss.
Great. Now we come to the last thing. So before that, um, so it is obvious now. So once you have actually completed this particular exercise, it's quite easy to see that if a function f happens to be 1, 1 and it is equivalent to another function g, then their equivalent implies that one is 1, 1 only when the other one is 1, 1. And since it's an equivalence relation, so if f is equivalent to g, g is also equivalent to f. Which means if f is 1, 1 implies g is 1, 1, g is 1, 1 implies f is 1, 1. So these are equivalent. F is 1, 1 if and only if g is 1, 1. Similarly, f is surjective if and only if g is surjective. When f and g are equivalent. No matter which particular equivalence they come from. If they are coming from this or this or this does not matter. But if they are equivalent in any of these senses, then one oneness of one is implies and implied by the one oneness of the other, and same holds for the surjectivity. Okay, so
Yes.
due to this due to this, the notions of injectivity and surjectivity are compatible with the equivalence relation. Okay, now let me make a new share. Huh? Why? Wait. So just a second, huh? Hmm. So is this visible?
Yes, miss.
Is it like nicely enough visible, or should I zoom it?
No, it's fine.
You're able to read, right? Okay.
Yes.
So the 12-fold way now is represented through this particular table, depending on whether the elements of n are distinguishable or non-distinguishable, whether the elements of x are distinguishable and non-distinguishable. Okay. And so this is the 4 restrictions which you had on when to consider two particular functions to be same or not. And then the other type of restriction was on the type of f, which is you take any f, or you take injective f, or you take surjective f. Right? This is what we talked about in the beginning. Correct?
Yes.
So first of all, when we say the number of injective F, you really mean the number of injective F, or rather the equivalent. So injective F, this particular number which you see here, is corresponding to this equivalence class DD. So the cardinality of this DD, which gives you injective F, is this. Clearly DD is a total of this plus this plus this. Or actually not, sorry, that's a wrong this thing. Okay, let me not say that as of now. What I'm saying is that, so when you deal with the equivalence class generated by the functions when the elements of n and elements of x both are treated to be distinguishable, there you will have all types of functions. In all those types of functions, inside this equivalence class itself, there will be injective functions, right?
Yes.
And there will be surjective functions. And there are then functions which are neither injective nor surjective. So everything which is injective falls here, everything which is surjective falls here, and it has much more than this. That's a correct statement to make. Is that right?
It would be the first column, right? In all the cases.
Yes.
Okay.
First column as in third column, right?
Yes.
Right. So you, when we write a number here in any of this box, it is counting the number of inequivalent functions in that equivalence class. Okay. So this has already given rise to an equivalence class. Inside this equivalence class, you count the number of inequivalent functions. Okay. So when
Yes.
both of the elements of n and x are distinguishable, you see that for any a you choose in n, f of a can be chosen in x many ways because it has x choices, f of a. And this is true for
Yes.
any element a of n. Therefore, the total number of functions that are there are exactly x raised to n. All right.
Yes.
So these numbers which you here see, these are these small numbers here. So you see 1, 2, 3, 4, 5, 6, and so on up till 12. So here are these 12 entries, which gives you the 12-fold way. Okay. Now,
Yes.
if the second one which I see here, so I have to count the number of injective inequivalent functions f from the set of distinguishable n many elements to a set of x many distinguishable elements. Injective, which means as soon as the first element of this set is sent to something here, the next element can be sent in one lesser way, right? So if f of a1 is can be sent in x ways for the next element, so n, since it is distinguishable, you can write elements to be a1, a2, an. So f of a1 has exactly x choices, which was the cardinality of x. So once this is fixed, one of the elements from capital X has been chosen, f of a2 now has x minus 1 choices. F of
Yes.
a3 will have x minus 2 many choices, and so on. So f of an will have x minus n plus 1 choices. So the number of functions is going to be x, x minus 1, x minus 2, and so on till x minus bracket n minus 1, which is x minus n plus 1. But what is this number? This is nothing but the n factorial of x. Remember, we did this when we did the number of fields. We counted the number of subspaces of fqn of cardinality k.
Yes.
So this is that notation. You have n factorial of x. Okay. Now coming to the third element, it says you have to count all the surjective functions. So before that, there is some discussion, or actually this you should be able to read quite quickly because we have done Stirling numbers earlier itself. But let me just go through it very quickly. So a partition of a finite set n is a collection pi into the blocks b1, b2, bk. So far we have been seeing partition of a number, right? Now you have partition of a finite set, correct? So when you did the partition of a number, you had parts. Now when you're doing partition of a, so each part actually, if you see, so if let's say some part was equal to 5, you actually meant that there are 5 units there, correct? So that equivalently here would mean that a block is of size 5. Isn't that so?
Yes.
So with that, keeping that notation intact in our head, what we can generalize our partition of a number to partition of a finite set as a collection pi of k blocks b1, b2, bk of subsets of n such that each of these blocks is non-empty. Okay, we throw away the redundant ones. That's how we even came to the word parts there. Parts are those particular coefficients in the lambda which are having value non-zero. Remember? And well, since there,
Yes.
when we wrote that partition, it was already giving you a summation to be equal to n. Here, the equivalent thing is achieved by saying that the intersection has to be empty and the union has to be n. If intersection is non-empty, this union may have different cardinality and this can have different cardinality. So you want to really write n as a disjoint union of these non-empty sets. That is what a partition of a finite set really means here. Okay. So we call Bi a block of pi and we say that pi has k blocks denoted mod pi as k. Defined S and k to be the number of partitions of an n set into k blocks. So S and k is the number of partitions of an n set into k blocks. The number S and k, this we have already done if you remember. It's called the Stirling number of the second kind. Which Stirling number did we do? Okay, look up your notes
That
from
was the
the
that was the first kind, right?
first kind. And why? I mean, so you see the analogy why that would have been the Stirling number of the first kind and this one is Stirling number of the second kind?
Yeah, that was partition of numbers and this was partition of sets.
This is partition of sets. So in the contrast, if you try to put these numbers, then you can also see that the number of surjective functions from distinguishable set to distinguishable set is the cardinality x factorial times Snx. Okay. Similarly, all these other entries are also explained, which I have here. So first just see that. So fourth is elements of n are non-distinguishable, elements of x are distinguishable. Okay. So the balls, so remember elements of n we said as balls and elements of x were boxes. So balls are indistinguishable. So we are only interested in how many balls go into each box b1, b2, bx. Right? Fourth is the one which corresponds to any f. There is no restriction on the function f. So how do you do this? If V of bi balls go into box bi, then V defines an n element multiset on the set X. Correct?
Yes.
And then how many such multisets are there? X multi-choose n. You have to choose n element subset from X. Right? You just have to take something from the X and assign it to your element of n. But since the element of n are indistinguishable, which element comes and gets attached does not make a difference. So you just say that no matter what happens, you just tell me there are, in some way or the other, you just partition your X boxes into n many places, and then I will put my balls there in whatever way I like. And that is exactly done in the X multi-choose n many ways. So this number, when the n is having indistinguishable elements and the elements of X are distinguishable, the number of such functions is X multi-choose n. And then once this you understand, injective f is X choose n. Very clearly. Each box now contains at most one ball. So the multi-set concept is ruled out. Now you have to bring this down to a set. Therefore, it is X choose n. Fine.
Yes.
Oh, I'm running out of time. There's another meeting I have to start. Okay, guys. So I will leave this here. Can you read this up? This is similarly like the description of other entries. And one last thing which I will say is that so the 12-fold way which we saw here can be generalized in many ways. And there are things like 30-fold way. There is something called a even bigger way where you do like here we had two types of restrictions, two major restrictions, and within each restriction there were further classifications, right? When these differ, then you have different kind of fold problems. So 12-fold way because there are 12 equivalence classes of functions in total, which you can deal with. So when you have here a different way or here a different way, the number of columns and rows will change, and accordingly you will have a different fold way problem. Okay, so all those are there which are not part of this particular course, but if at all you are interested, they you can read them up from chapter 7 of this particular book. So yeah, this thing ends here. And next thing which I have to say is that, so next lecture we will deal with the sieve methods, and I think in the Moodle I have uploaded only chapter 1 of enumerative combinatorics, right? Or it has 1 to both, I don't remember. So anyway, the main point is, I will, if it does not have rest of it, I will put the next part and we'll see that in the next lecture. Okay.
Okay.
Yeah, this I have uploaded till chapter 1 only. So I will upload the chapter 2 of this book. I'll upload chapter 2 of this book, and next lecture we'll cover that. Next 2 lectures we'll cover that. Okay? Chalo.
Okay.
Bye bye.